Introducing SharpDepth, sharpening metric predictions using diffusion distillation. We propose a novel method to enhance metric depth maps by refining predictions with diffusion-based distillation. SharpDepth produces sharper, more detailed depth estimates, pushing beyond the limitations of traditional approaches. This task involves predicting real-world distances, in meters, from just a single RGB image. Unlike relative depth, which only captures depth ordering, metric depth provides absolute scale. This makes it crucial for downstream 3D applications like SLAM, novel view synthesis, and 3D tracking. Models like UniDepth do a great job here. They can infer accurate per-pixel distances that align with real-world scale, even without access to camera intrinsics at test time. These models are typically trained on real-world datasets, where depth ground truth is captured using sensors like LiDAR, stereo rigs, or structure from motion. But unfortunately, this ground truth is often incomplete or noisy. The examples shown here illustrate some common issues. Transparent or reflective surfaces confuse depth sensors, repetitive patterns throw off stereo matching, and dynamic scenes introduce inconsistencies in structure from motion pipelines. Therefore, this leads to a loss of fine detail, causing oversmoothing effect, especially around object boundaries. Recent advances in this space have taken advantage of powerful diffusion models, originally designed for text-to-image generation. By fine-tuning these models on synthetic depth data, we can leverage their rich visual priors to produce sharp, detailed affine-invariant depth predictions from a single image. As shown here, these models are capable of capturing extremely fine structures, from fur and folds to tiny architectural features, with minimal training data. But there's a trade-off. These methods only predict relative depth. The depth values are normalized and lack a true metric scale, which limits their utility in many real-world tasks that require absolute positioning, like robotics, SLAM, or 3D scene reconstruction. So we have two complementary strengths. Metric models are accurate but smooth, and diffusion-based models are sharp but not metrically grounded. SharpDepth aims to combine the best of both worlds. In this paper, we propose a method to enhance the sharpness of monocular metric depth predictions. Our approach introduces an additional network that acts as a sharpener, refining the output of a base metric depth estimator. Remarkably, we achieve this without requiring ground truth depth and with minimal training cost, while still producing accurate, high-quality depth maps. First, we begin with an RGB input image. Using a diffusion-based depth estimator, we obtain a highly detailed affine-invariant depth map, while a metric depth estimator provides an accurate, real-world metric depth map. To refine these outputs, we introduce a SharpDepth model. A naive solution might be to directly input one of the depth maps into the model. However, this leads to an ill-posed learning problem, where the model simply reproduces the input without learning meaningful refinement or fusion. Similar issues arise with other straightforward approaches. To address this, we propose a noise-aware gating mechanism that intelligently combines the two depth maps. Given the input image and two corresponding depth maps, we first align their values and compute a difference map. Using the formulation shown in the red box, we generate a blended depth map. The key intuition is: in regions with high disagreement between the two depth maps, bright areas in the red circle, we destroy the unreliable information and allow SharpDepth to reconstruct these areas. In regions with low disagreement, highlighted in the purple area, we preserve and retain the reliable information. This selective fusion allows the model to focus on reconstructing uncertain regions while keeping others untouched. At the final stage, we obtain a noise-aware latent representation, which is fed into our SharpDepth model to produce a sharpened metric depth map. To supervise depth accuracy, we use the metric depth output from the metric depth estimator and compute a reconstruction loss. Importantly, we apply a difference-based weighting mask to this loss, emphasizing regions where the two input depth maps disagree, guiding the model to focus on areas that need refinement. To supervise sharpness, we introduce a score distillation sampling (SDS) loss, where the teacher is the diffusion-based depth estimator. This loss encourages the SharpDepth model's output to match the distribution of the diffusion-based depth input, helping it preserve the high-frequency detail and structure characteristic of diffusion-generated maps. Together, these losses guide SharpDepth to produce depth maps that are both accurate in metric scale and visually sharp. We perform detailed quantitative results, comparing with many state-of-the-art models. When comparing metric accuracy, our depth maps demonstrate competitive accuracy in zero-shot metric depth estimation. Compared to recent methods like Depth Anything v2, which also emphasize sharpness, our approach outperforms them in many scenarios. While we do not expect to surpass our teacher model, UniDepth, our results are only marginally lower, as shown in the table. In terms of sharpness accuracy, we benchmark our model on several synthetic and real-world datasets. While Lotus, our teacher model for a fine invariant depth, sets a high standard that we do not expect to surpass, our method achieves the highest ranking in the metric depth category. Across multiple datasets, our model consistently delivers superior results. In the graph, we show depth boundary error completion, measuring sharpness accuracy, and root mean squared error, measuring depth accuracy. Our model may not achieve state-of-the-art accuracy in either metric alone. However, it achieves the best balance between sharpness and accuracy, effectively pushing the current Pareto frontier forward. For qualitative comparison on Kitty, our model not only achieves sharpness competitive with UniDepth-aligned Lotus, but also matches the accuracy of UniDepth itself. In the error map of UniDepth-aligned Lotus, large red regions indicate high errors, whereas our model's error map closely resembles UniDepth-S, with predominantly blue areas indicating low depth error. On the indoor NYU dataset, we observe results similar to Kitty. Our depth accuracy matches that of UniDepth, while our depth sharpness is comparable to UniDepth-aligned Lotus. In the final example, UniDepth-aligned Lotus fails to capture the bottom of the lamb, and UniDepth produces blurry edges around it. In contrast, our method captures both the sharp boundaries and the complete shape, including the bottom of the lamb. Next, we show the generalizability of our method. We run on several images captured by mobile device with high resolution. Our method achieves highly detail and high accuracy depth image. Here is some more example with different aspect ratio. Overall, SharpDepth can obtain metric depths with sharp boundaries. We also collect some in-the-wild internet image to evaluate qualitative results. Our model consistently output highly detailed and accurate depth map. In terms of 3D point cloud reconstruction, our method demonstrates a significantly higher level of detail. For example, in the durian scene, our reconstruction clearly captures the spikes on the shell, while UniDepth produces a flat, oversmoothed surface. Similarly, in the keyboard example, our model preserves the contours of individual keycaps, whereas UniDepth renders them as a flat plane. We further show our reconstruction point cloud from other examples. We also validate the effectiveness of our method on a downstream task, DenseLam, by integrating our estimated depth maps into MonoGS. By providing high-detail depth inputs, our model helps reduce visible artifacts in the rendered images. Quantitatively, we observe improvements across key metrics, including PSNR, SSIM, and LPIPS, confirming the benefit of our sharper and more accurate depth predictions in practical applications. Thank you for listening to our presentation. Please visit our website for more information.